Hi, my name is Francesco and I'm a PhD student at the Institute of Astronomy in Cambridge, under the supervision of Professor Cathy Clark. In this video I'm introducing the two main results of my master's thesis project, which was mainly developed in Leiden under the supervision of Dr. Giovanni Rosotti and in Milan under the supervision of Professor Giuseppe Lodato. As the title suggests, our work focuses on the evolution of the solids in planet-forming disks in binary systems. This is an interesting research topic for several reasons. First of all, it is widely known that more than half of the main sequence stars are part of multiple stellar systems. Secondly, more and more exoplanets are detected in binaries, despite the theoretical impediments for planet formation in this hostile environment. In our research, we focused on dust evolution for three main reasons. Firstly, solids are the main components of the exoplanets. Secondly, the dust dominates ALMA observations. Last but not least, to our knowledge, no theoretical work has focused on dust evolution in circumstellar disks in binary systems on secular timescales. To address this question, we ran several numerical simulations. The code we used is presented in Bot et al. 2017 and was also employed in Rosotti et al. 2019. As for the gas, we solved the viscous evolution equation, while for the dust we employed a two-population model of Bernstein et al. 2012. Binarity is taken into account imposing a zero-flux outer boundary condition on both the gas and the dust, as previously done in Rosotti and Clark 2018. Let us first focus on the numerical results. Our main expectation is that both the gas and the dust evolve faster in binary disks than in those around single stars. This is confirmed in the following figure, in which the dust-to-gas mass ratio, m dust over m gas on the y-axis, is plotted as a function of the disk truncation radius, r trunk, on the x-axis. The figure is color-coded according to the initial disk radius r0 and refers to t 1 million year. Each subplot is characterized by a different disk viscosity, with alpha increasing towards the right. Let us consider the alpha 10 to the minus 3 and r0 10 AU case. As the figure suggests, two regimes can be identified. As long as our trunk is less than 100 AU, disks in binaries, the blue dots, lose more dust than disks in singles with the same parameters, the black cross. On the contrary, for a trunk bigger than 100 AU, binary disks behave as singles. Similar trends can be witnessed changing R0 and in the alpha 10 to the minus 4 case, even though the truncation radius at which the saturation occurs changes as more dust is stored in the outer disk and because of an overall slower disk evolution, respectively. As the viscosity increases, saturation never occurs. Moreover, more dust is retained than in the case of lower alphas, due to the inner disks being in the fragmentation-dominated regime. However, although the less viscous disks lose more dust within the first million year due to a faster radial migration of the grains, the most viscous ones leave less because of a smaller gas evolution timescale. Moreover, the rapid depletion of the solids in binary disks suggests that planetesimal must form fast for planet formation to be viable. Let us move to the observational implications. In Taurus, Manara et al. Found that the observed disk sizes are too small to be explained without invoking very high eccentricities. To compare our model predictions with those observational results, we compute disk dust sizes from our models at ALMA wavelengths. In this figure, the radius enclosing the 68% of the total dust flux, Rf, on the y-axis, is plotted as a function of the disk truncation radius, r trunk, on the x-axis. The dashed gray line refers to our zero eccentricity models, and the shaded gray area is the 1 sigma model spread. The same quantities computed assuming zero eccentricities are overplotted for multiple stellar disks in Taurus, blue dots, and Ophiuchus, orange dots. As the figure suggests, our zero eccentricity models naturally explain why disk dust sizes are smaller than the truncation radius once dust radial drift is taken into account. To sum up, in our work we showed that planet-forming disks in binaries evolve faster than those around single stars, implying that if planet formation takes place, it must be fast. Finally, the comparison with the observations suggests that disk dust sizes are compatible with low eccentricity models once radial drift is taken into account.